just want to tie up a couple things about this problem of the week. I'm not really going to get into the details of the algebra. If you had trouble with that, we can certainly talk about it. The short summary here, f of x plus h, when you put that into the sine function, you have sine of x plus h. That's when you have to get into your sum of two angles formula and then work it on from there. These limits, these you're going to encounter in calculus and how to deal with it specifically. We just kind of cheated. But what's going on here? Cosine of 0 we know is 1. 1 minus 1 is 0. And if you put 0 in for h, you get 0 over 0. That's called indeterminate. Nothing divided by nothing is not infinity, and it's not 0. We really can't tell. And sometimes it actually equals something else, like in this case. Both of these actually do have a value they equal, and we found that by playing around with really small numbers. So again, these are scenarios in calculus you'll get an explanation for. You'll learn some methods of how to deal with that. So hopefully the algebra went okay. I did want to show you this. Now that you've explored enough, the slopes of these sine, cosine graphs, all this. So here's a sine graph, and hopefully you're starting to get familiar with this. You can kind of look at it and tell. So the slope, if you graph all the slopes of this sine wave, you get the cosine curve. So let's kind of look at how we can quickly tell. So at 0, we have a slope of 1. At pi over 2, we have a slope of 0. At pi, a slope of -1. At 3 pi over 2, slope of 0. So a curve that has a value of 1, 0, -1, 0, that's the cosine curve. All right. Now, if you take the slopes of the cosine curve, well, you have 0, and then -1, and then 0, and then +1. That's the negative sine curve. It has values of 0, -1, 0, 1 at these respective intervals. All right. You probably can see where this is going. If you take the slopes of the negative sine curve, -1, 0, 1, 0. So what has values of -1, 0, 1, 0? That's the negative cosine curve. All right. So you are getting a cycle here, and it only has 4 parts. It starts back over at this point because if you look at the slopes of negative cosine, 0, 1, 0, -1. That's your sine graph. These slopes, 0, 1, 0, -1, those are the y values you get back on the sine curve. So it does kind of go, it is a cycle of 4. If right off you're kind of thinking, wait a minute, that I cycle had 4 parts too, there are some comparisons you can make. We graphed recently the I cycle going kind of 90 degrees every time you multiply by I if you go into that complex plane, which etches out a circle. Every time you multiply by I, you go 90-degree rotation, and that's exactly what's happening with each one of these. I mean, sine and cosine, they're the same curve. Cosine just gets shifted 90 degrees to the left, and negative sine is cosine shifted 90 degrees to the left as well. So these 90-degree shifts, they are similar. There are connections, and you could certainly get into all sorts of things that why the I cycle and why this is connected. But this is a pattern you will see in calculus, and I'm trying to get you to kind of have this memorized. So when you get to calculus, it's like, oh, okay, that makes perfect sense. And it kind of gives you, you're ready to hit the ground running when you get into what's really going on deeper here. And then just to show you, this time of year, it always kind of makes me think about this. Here's a sunrise sunset chart, and I won't go through all the data. You don't really need to see all that. But what I did make is a graph of it. So if we look at, and this is, winter starts December 21st or so it's like 9 days shifted. We could get into all the shifts and how the curve would be shifted. But if we graph a year, the length of the day of a year is basically a negative sine wave. Basically starts at negative cosine wave. Starts at -1, then 0, 1, so on. So if you take all the slopes of that, 0, 1, 0, -1, that etches out a sine wave. So the rates of change. So what I'm looking at, if I look at the length of the day, days are getting longer right now. And about this time of year, the first day of spring is like the maximum acceleration for that. If it felt like the days were not changing much back around New Year's, they weren't. They were barely changing at all. And now they might have been changing by a matter of seconds per day. It just felt like it was barely changing. Now we're changing like 2 minutes per day. Every day is a couple minutes longer than the one before it. So the length of the day will not change faster at any point until the first day of fall, when it's getting shorter really fast. And that's also why you might notice in around end of August, early September, it just seems like the days just all of a sudden got really short. It's because they're getting shorter at the fastest rate you'll see all year. So that is something you might pay attention to and notice. But anyway, if we graph out the rates of change, we get a sine wave here. And then I just did one more rate graph because this is kind of hard to process. I was trying to make sense of it, but the change of the change, like the acceleration of the length of the day, and since mine it's in near seconds, which is pretty precise. That's why it's getting kind of a weird shape. But what I want to point out, if you take the changes of the rate of increase, slope of 1, slope of 0, -1, that's a cosine looking graph. And if you plot those out, I don't know, it's not very smooth, but it does make a cosine graph. So just a real life application of where you see this cycle of the sine, cosine, negative cosine show up. So just something a little extra to throw out there for you. Let me know if you had issues with the algebra of the problem, and I'll help you with that.